The gasoline in your tank never existed underground. And despite what the tallest structure in a refinery suggests, it is not finished in the distillation tower. Early refiners sometimes discarded some of its lightest fractions. Today, those molecules are split, rearranged, and blended into formulas that change with the season and where they are sold. One early shortcut to higher octane even killed the workers producing it. So where does crude oil finally become gasoline? To find that moment, we are going to follow one barrel of crude oil through the entire process. By the end, that barrel will no longer exist as a single substance. It will have been washed, heated, vaporized, divided, broken apart, rebuilt, cleaned, recombined, tested, and transported. Some of it may become diesel, jet fuel, propane, asphalt, lubricant, or chemical feedstock. But one part will complete a transformation that the oil industry spent more than a century learning to control. And that transformation begins with a product almost nobody wanted. When the first commercial oil wells appeared in Pennsylvania during the 19th century, refiners were primarily searching for kerosene. Electric lighting did not yet exist on a useful scale, and kerosene offered a relatively affordable source of illumination. Distilling crude oil also produced lighter, more volatile fractions such as naphtha and what would later be recognized as gasoline range material. But there was no enormous fleet of automobiles waiting to consume them. Some early refiners had little use for these fractions. Part of the material was discarded, burned, or sold into much smaller markets. The molecules had potential. The market did not. Then two technologies reversed their value. Electric lighting began reducing the demand for kerosene lamps, while the internal combustion engine created a rapidly expanding need for a volatile liquid fuel. Gasoline had not suddenly changed. A machine had finally appeared that needed it. This created an immediate manufacturing problem. Simple distillation could recover only the gasoline range molecules already present in crude oil. As automobiles multiplied, refiners could not make the distillation tower taller and wait for more gasoline to appear. They needed to create more of it from the same barrel. But before our barrel reaches a furnace, a technician takes a sample and asks a question most drivers never consider: is this the right crude oil for this refinery? Crude oil is not one universal black liquid. Its properties change depending on where and how it formed. Some crude is light, containing a larger proportion of lower density hydrocarbons. Other crude is heavy, with more large molecules and residual material. Crude may also be described as sweet or sour. Sweet crude contains relatively little sulfur. Sour crude requires more treatment to remove sulfur compounds. Heavy or sour crude is not automatically useless. Our complex refinery, equipped with cracking, coking, hydrogen, and sulfur recovery capacity, may convert it into valuable fuels. A simpler plant may operate more efficiently with lighter, sweeter crude. Refineries can also mix different feedstocks, but each facility has physical and economic limits. Laboratory information known as a crude assay helps predict how the oil will behave. It describes density, sulfur, boiling ranges, metals, and the likely yield of different fractions. Two barrels with the same volume may therefore take very different routes through the refinery and produce different amounts of gasoline. The first decision affecting our fuel may happen before the oil enters a processing unit. Once the crude is accepted, it still cannot be sent directly into the distillation furnace. Hidden inside are substances that can slowly disable the refinery from within. Crude oil often carries tiny droplets of water containing dissolved salts. It may also contain suspended solids and trace metals. Left in the stream, salts contribute to corrosion. Solids accumulate inside heat exchangers and restrict flow. Metals can poison the expensive catalysts needed farther downstream. Before the refinery uses extreme heat to create gasoline, it must remove something almost too small to see. The crude is mixed with hot water and, when necessary, chemicals that help separate the water from the oil. The salts dissolve into the added water. Inside an electrostatic desalter, a high-voltage field encourages tiny water droplets to join together. These larger, heavier drops settle toward the bottom, carrying salts and contaminants with them. Cleaner crude leaves from the top. Contaminated water is removed for treatment. Our barrel has now been washed, but it is still crude oil. Not 1 gallon of finished gasoline exists yet. Pumps move the desalted crude through heat exchangers, where it absorbs energy recovered from other hot refinery streams. This reduces the amount of fuel the furnace must burn. The crude then enters a direct-fired heater, where its temperature may rise to roughly 650 to 700 degrees Fahrenheit, depending on the feedstock and refinery. At those temperatures, most of the mixture begins to vaporize. The hot liquid and vapor enter the lower part of an atmospheric distillation column, a steel tower that may rise more than 100 feet above the refinery. Inside is a vertical ladder of temperatures. The bottom remains extremely hot. Each level becomes progressively cooler toward the top. As hydrocarbon vapor rises, different molecules condense at different heights according to their boiling ranges. Heavy residue remains near the bottom. Above it, the refinery draws heavier gas oils. Higher still are diesel-range distillates and kerosene. Naphtha and other light fractions rise farther before condensing. The lightest refinery gases travel toward the top. From the outside, this appears to be the moment crude oil becomes gasoline. It is not. Distillation is a sorting process. It finds what is already inside the crude. The naphtha collected from the tower may overlap part of the gasoline boiling range, but it is not necessarily ready for an engine. It may have insufficient octane, too much sulfur, the wrong volatility, or a composition that fails modern emissions requirements. Meanwhile, much of our barrel remains trapped in heavy fractions that cannot be poured into a car. The tower has separated the crude, but it has not solved the shortage that emerged with the automobile. To create more gasoline, refiners had to stop treating nature's molecules as fixed. Heavy gas oil from the distillation system is sent toward one of the refinery's most important conversion units, the fluid catalytic cracker, or FCC. The best way to visualize cracking is to imagine extremely long molecular ropes being cut into shorter pieces. Heavy hydrocarbons contain larger structures that are difficult to use as gasoline. Cracking breaks them into smaller, lighter molecules. The physical process begins when heavy feed is preheated and brought into contact with a stream of extremely hot catalyst particles. The catalyst is so finely divided that vapor can make it circulate almost like a fluid. As oil and catalyst rush through the riser, the heavy molecules vaporize and crack. Long hydrocarbon chains split. New structures form. Material that entered as heavy gas oil emerges as a mixture containing gasoline-range hydrocarbons, liquefied petroleum gases, lighter gases, cycle oils, and other products. But cracking creates a new problem almost immediately. Carbon-rich material called coke accumulates on the catalyst and reduces its activity. The refinery solves this without stopping the process. Used catalyst flows into a regenerator where the coke is burned away. The burning coke reheats the catalyst. Regenerated catalyst then returns to the riser and meets another stream of oil, crack the molecules, clean the catalyst, recover the heat. Repeat. Operators in the control room monitor the balance between reactor and regenerator. The system contains hot hydrocarbon vapor, catalyst dust, combustion gases, and material capable of igniting if containment fails. Temperature, pressure, oxygen, and catalyst circulation must remain within carefully defined limits. When the system works, it changes what a barrel can produce. A standard barrel of crude oil contains 42 gallons, yet a refinery in the United States can produce approximately 45 gallons of petroleum products from that barrel. No matter has appeared from nowhere. Many of the finished products are less dense than the crude that entered, so their combined volume is greater. This is called processing gain, and average roughly 19 to 20 gallons from that barrel may become motor gasoline, although the actual yield changes with crude quality, refinery configuration, operating decisions, and market demand. This is the first major answer in our journey. Distillation finds gasoline-range material. Cracking manufactures additional gasoline components from molecules that were originally too heavy. The refinery has finally learned how to make more gasoline from the same barrel. But quantity is no longer the hardest problem. The next challenge will lead engineers to a shortcut that protects millions of engines while exposing millions of people to poison. Inside a gasoline engine, the piston compresses a mixture of fuel and air. That compression raises pressure and temperature. Ideally, the spark plug ignites the mixture at precisely the correct moment. A flame spreads across the cylinder and pushes the piston downward. But under the wrong conditions, part of the fuel-air mixture can auto-ignite too early. Pressure waves collide inside the cylinder, producing the metallic ping known as engine knock. Repeated severe knocking can damage an engine. This is why gasoline needs octane. Octane rating does not directly measure how much energy the gasoline contains. It describes the fuel's resistance to auto-ignition under compression. Higher octane gasoline can tolerate more demanding engine conditions before knocking occurs. Building that resistance requires another molecular workshop. Cracking is like cutting a long rope into shorter pieces. Isomerization keeps the same basic pieces but rearranges their shape. Imagine rebuilding a structure from the same Lego bricks, changing a straight line into a more branched form. The number of atoms may remain the same, but their arrangement can improve anti-knock performance. Alkylation performs the opposite kind of operation. It takes small molecular fragments produced elsewhere in the refinery and joins them into larger, compact, highly branched structures. The resulting alkylate is a valuable high-octane gasoline component. Catalytic reforming makes a broader set of structural changes. Low-octane naphtha is heated and passed through reactors containing catalysts that may include platinum. Molecular structures are rearranged, creating high-octane reformate. The process also produces hydrogen, which can be captured and used elsewhere in the refinery. The same carbon and hydrogen atoms can behave differently simply because they have been rebuilt into different shapes. These molecular operations sound almost elegant. The equipment carrying them out is not gentle. Reforming involves high temperatures, pressurized hydrogen, and flammable hydrocarbons. Alkylation may use sulfuric acid or hydrofluoric acid. Hydrofluoric acid is intensely corrosive and toxic. Under certain release conditions, it can form a dangerous vapor cloud. A process that creates a valuable gasoline component, therefore depends on keeping every hazardous material sealed inside vessels, pumps, valves, and piping. By now, our original barrel has lost its identity. One fraction has been cracked, another has been reformed. Small molecules may have entered an alkylation or isomerization unit. Each stream now contributes a useful property, but none is finished gasoline. And the search for octane is about to expose the darkest part of the story. During the early 1920s, researchers discovered that adding a small amount of tetraethyl lead could dramatically reduce engine knock. It was cheap, effective, and attractive to an automobile industry seeking more powerful engines. The danger appeared almost immediately among the people producing the additive. Workers exposed to concentrated tetraethyl lead developed devastating neurological symptoms. Some experienced confusion, hallucinations, loss of coordination, convulsions, and severe changes in behavior. An EPA historical account reports that 15 workers died at facilities in New Jersey and Ohio during 1924. The substance's toxicity was no longer hypothetical. Yet leaded gasoline spread across the world and remained in widespread use for decades. Every engine burning it released lead compounds through the exhaust. The contamination settled into streets, soil, household dust, and the air people breathed. Children were particularly vulnerable because lead exposure can permanently damage the developing brain. Leaded gasoline created a brutal contradiction. It protected engines from knock while exposing human beings to a neurotoxic metal. Its removal did not happen in one sudden decision. In the United States, efforts to reduce lead in gasoline began during the 1970s. Public health evidence mattered, and the growing use of catalytic converters created another practical reason for change. Lead damages the catalyst used to control other vehicle emissions. Unleaded gasoline became increasingly available. Leaded gasoline for on-road vehicles was eventually prohibited in the United States at the beginning of 1996. The global transition took much longer. In 2021, Algeria became the final country to stop selling leaded gasoline for automobiles, completing the worldwide phase-out of leaded road fuel nearly a century after its introduction. But removing lead did not remove the need for octane. Refiners still had to prevent engine knock. Now they had to do it through molecular conversion, improved blending, and carefully selected components rather than a toxic shortcut. Octane is only one part of the final specification. The refinery must also deal with sulfur. Sulfur compounds can travel with crude oil and remain inside intermediate streams. They contribute to harmful emissions and can interfere with vehicle pollution control systems. Their removal commonly involves hydrotreating. In a hydrotreater, a petroleum stream is mixed with hydrogen, heated, and passed through a catalyst under pressure. Sulfur compounds react to form hydrogen sulfide, which is then separated from the cleaned hydrocarbon stream. But removing sulfur from gasoline does not make the sulfur disappear. It simply moves the problem. Hydrogen sulfide is highly toxic and must remain contained. Gas treatment and sulfur recovery systems can process it further, converting it into elemental sulfur. Recovered sulfur may become feedstock for sulfuric acid, fertilizer production, and other chemical uses. This does not mean that nothing is wasted in a refinery. Refineries still generate wastewater, emissions, coke, spent materials, and other streams requiring treatment or disposal. The real achievement is that a contaminant once hidden inside crude can be isolated, transformed, and managed instead of being allowed to remain in the fuel. The path is also less linear than it appears. Some streams are treated before conversion to protect sensitive catalysts. Others are treated afterward to meet product standards. Material may move forward, sideways, or back through the plant depending on its composition. A refinery is not a single assembly line. It is a network of interconnected decisions. At last, the useful streams begin moving toward one place. Straight-run material contributes one set of properties. FCC gasoline provides volume and other characteristics. Reformate contributes octane. Alkylate and isomerate improve anti-knock quality. Butane may be useful in carefully controlled amounts. Ethanol can provide oxygen and additional octane. Detergents and other approved additives contribute specific functions. This is the moment gasoline finally begins to exist. Modern blending may use computer-controlled systems that inject precise quantities of multiple components into a moving stream. The refinery is not following a simple fixed recipe. It is solving a constrained optimization problem. The blend must reach its octane target without exceeding limits for sulfur, benzene, vapor pressure, and other regulated properties. It must behave properly inside the engine, remain stable during storage, meet emissions requirements, and survive transportation without drifting outside specification. Changing one component can affect several properties at once. Adding a high-octane stream may also change volatility or aromatic content. Removing sulfur may reduce components that previously contributed octane. Adding ethanol can raise octane while altering the behavior of the final blend. Every improvement creates another variable that must be balanced. This is why regular, mid-grade, and premium are not simply different labels attached to identical fuel. Their main retail distinction is anti-knock rating. Engines designed for higher compression or other demanding operating conditions may require greater resistance to auto-ignition. Higher octane does not automatically mean that the fuel contains more energy. Putting premium gasoline into an engine designed for regular does not guarantee more power. It simply provides a level of knock resistance that the engine may or may not need. The recipe also changes with the weather. Gasoline must vaporize before it can mix effectively with air. In cold conditions, greater volatility can help an engine start. In hot weather, gasoline that vaporizes too easily can increase evaporative emissions and create operational problems. Summer gasoline is therefore generally blended to lower volatility than winter gasoline. The change can involve altering the proportions of more volatile components such as butane. Location matters as well. Climate, altitude, regional emissions programs, local regulations, available blend components, and ethanol requirements can all influence the finished formula. Two samples, sold as regular gasoline in different regions or seasons, can fulfill the same broad purpose while containing different proportions of individual hydrocarbons. And, in some markets, gasoline may not be completely finished when the petroleum blend leaves the refinery. A refinery can produce a blend stock designed to receive ethanol later at a distribution terminal. The terminal combines the petroleum blend with the required oxygenate and additive package before the gasoline enters a tanker truck. This finally closes the central mystery. Crude oil does not become finished gasoline in the well. The desalter, the distillation tower, the cracker, or the reformer. Those stages create fractions and possibilities. Finished gasoline appears when carefully selected streams are combined into a blend that satisfies every required property at the same time. But a mathematically correct recipe is not enough. The fuel must prove itself. A technician takes a sample from the batch. The laboratory measures properties, such as sulfur, vapor pressure, density, distillation behavior, and possible contamination. For octane, standardized methods use special test engines operating under controlled conditions. Research octane number and motor octane number. Test the fuel under different operating conditions. At retail pumps in the United States, the familiar octane number is generally the average of those two results, displayed as R plus M divided by 2. The logic of the test is almost paradoxical. The refinery has spent enormous effort producing a liquid that burns easily. Now it places that liquid in an engine designed to push it toward the point where it might burn too soon. The gasoline earns its rating by resisting failure. If the sample falls outside specification, the batch does not continue simply because production is almost complete. It may be held, reblended, treated again, or redirected. Gasoline can look perfectly clear while being chemically wrong. Once certified, the fuel moves into large storage tanks. Pipelines, ships, barges, trains, or trucks then carry it toward regional terminals. Ethanol or brand-specific additive packages may be introduced as tanker compartments are filled. This final stage appears ordinary compared with a cracking reactor, but the danger has not disappeared. Gasoline releases flammable vapor. Liquid moving through loading equipment can contribute to static charge hazards. An overfilled compartment can spill fuel. Loading the wrong product can contaminate an entire delivery. Before flow begins, terminal operators verify product codes and compartment assignments. Tankers may be connected to grounding or bonding equipment. Overfill protection systems monitor the loading process. Vapor recovery lines can route displaced vapor into a controlled system instead of allowing it to escape freely. Gasoline has survived furnaces, reactors, hydrogen pressure, corrosive acids, and laboratory testing. A single, uncontrolled spark during its final journey can still ignite its vapor. The tanker carries the certified fuel to a gas station and transfers it into underground storage tanks. From there, the gasoline waits beneath the concrete until a driver lifts the familiar nozzle. The driver sees none of what came before. There is no sign of the crude assay that decided how the barrel would be processed. No sign of the salt pulled out by an electric field. No sign of the temperature gradient inside the distillation tower, the powdered catalyst circulating through the FCC, or the hydrogen removing sulfur. The pump reveals nothing about the workers killed by an early octane additive. The decades required to remove lead, the computer balancing summer volatility, or the laboratory engine deliberately pushing the fuel toward knock. It displays only a grade, a volume, and a price. That brings us back to the light petroleum fraction early refiners once struggled to value. The automobile transformed it from an unwanted byproduct into a scarce commodity. Cracking taught refineries to make more of it. Reforming, isomerization, and alkylation taught them to construct octane at the molecular level. Lead revealed how a technically effective formula could impose an enormous hidden cost. Treatment and regulation forced the industry to produce cleaner versions. Blending turned gasoline into a fuel that changes with the engine, the season, and where it is sold. A clear drop falling from the nozzle now carries the history of oil fields, refineries, laboratories, industrial accidents, public health battles, and countless decisions made at a scale too small for the human eye to see. Gasoline was not simply discovered and poured into the modern world. It had to be separated, manufactured, corrected, balanced, and proven. And it looks simple only because all of that complexity has already been solved before the nozzle reaches your hand.